Well, we're ready to start our problem set number 3. Again, this video defines the homework. It could be a little revised from what's in your lecture video. And let's go ahead and begin. First of all, it's worth 20 points, and we are going to ordinary exercises in your section 1.1. So when you turn in your pseudocode, it needs to be on a PDF file, or anything else that you need to submit with it would be on the same PDF file. But your MATLAB programs must all be on their own individual M files. So please do that for each of the problems. So here we are in problem 10. We are looking at this formula that was in the book. And some of you might look at that and go, ugh, that is a really ugly formula. And some might look at it and go, that's kind of a little cute formula. I don't know. But in any event, it's compact and it says a lot. The big sigma sign represents a summation. N is the upper limit of the sum, and I is an index that runs from the lower limit to the upper limit, and it's just taking on the values 1, 2, 3, and so forth. N, since it's the number of items in the sum, is composed, or each item is composed of what is inside it. We'll talk a bit more about that later. To do the MATLAB, you'll need values for A and B. So here's your A vector and your B vector, and from that you should be able to deduce what N is. We will be using in this problem, along with the next problem, our onion peeling methods that we learned in the course notes in the book and also in the lectures. And you will need to compute this term in such a manner that you don't waste any calculations, and onion peeling is one way to do that. On problem 11a, we're going to do almost exactly the same thing, starting with pseudocode. We have a polynomial of degree n, and we were going to evaluate that using two sets of parameters, both of which force it to be a polynomial of degree 100. The only difference between part A and part B is use x equals to 0.5 and x equals to 1.5 between those two methods. Finally, there is extra credit. I recommend doing the extra credit. Extra credit problems are not represented on either the midterm or the final, but they're a good way of bolstering your points up to keep your total homework score high. So let's go ahead and look at some hints for this onion peeling approach. Now here's our rather cryptic looking formula, which I am going to augment a little bit with parentheses. The reason I put the parentheses there is I want you to realize that everything inside the parentheses is a single term that will be used in an accumulation using this sigma sign. Well, let's start from the outside. We'll let I equal to 1. B sub I inverse just means the reciprocal of B1 in this case, since I starts off as 1. Or you could say 1 over B1. So the capital Pi sign stands for product. Again, it's indexed like that summation, but you're going from 1 to I. Well, initially I is just equal to 1, so this product isn't really doing anything. It's just picking off A1. So for I equals 1, this whole expression that looks kind of ugly isn't really that big of a deal. It's just A1 divided by B1. That's the very first term. When we come back around and put I equal to 2, we'll now take the reciprocal of B2 rather than B1, and we have two items in our product, A1 and A2. So the second term is just A1 times A2 divided by B2. And we continue to do that until we get to N. So this product is getting bigger and bigger and bigger, but it's pretty simple how it works. This is a written form of what I just said verbally. A1 over B1, A1 times A2 over B2, and so forth. The reason I'm writing it out this way is you can see how the onion peeling is going to occur. Instead of going from left to right, which would be a bit inefficient, we're going from right to left. The reason is you'll find yourself redoing multiplications that you've already done. Now there's some ways to get around that too, but the way we're going to get around it is to go from right to left and factor out as much as we can that's in common with the adjacent term. So if we look carefully at the last two terms, they're identical except there's one fewer term in the second to last term than there is in the last term. So let's just factor out what we can. We can take out a1 through an minus 1 out of each of these two terms, and we just get 1 over bn minus 1 plus an over bn. So we've simplified this considerably. Now, if we take a close look at an over bn, and I give it a name, I am going to start the process of building a generalized recursive formula. So it's the only difference between line 2 and line 3 is I've just done a name change. So now if we look at this expression, we see that, again, just like before, we have a lot in common between these last two terms. It's just that we can only go up to n minus 2 if we'd like to factor out common terms. So let's do that. We'll factor out a1 through an minus 2. And we put them out in front here. All we have left is 1 over bn minus 2, which is right here. And we do have an minus 1 left over, plus this term that we created previously. This is now the trick. We are going to substitute this expression, because it's going to come up over and over again, with another z term. We'll go to zn minus 1. So this term we will call zn minus 1. And then we will just plug it right back in here. And lo and behold, we've got something that looks an awful lot like what we did on the prior iteration. So if we continue this process, we can create new z sub n's that are involving the old ones. And we end up continuing to onion peel from right to left until there really isn't anything left but this simple little formula. So your job is to take what is clearly turning into a recursive relationship and generalize that. Another little hint is when you do so, you'll discover that you don't need to subscript the z's. You can take the last z, create this formula for it, create a new z by overriding the last one, and just plug it right back in again. Now let's take a look at some hints for problem 11a. There really isn't too much difference between this problem and problem 10. You're going to do the same thing. You don't need an a and b vectors like you did there, but you do need a value of x, and we are asking to run this twice, one with x equals 0.5 and one with x equals 1.5. So there they are. Your first problem is let n equal 100 and x equals 0.5, and then we will let n continue to be 100 and x will be equal to 1.5. Here is the abstract form of our polynomial, and we could write it down this way. And it's kind of nice to write it this way because you can easily see that there is an x in every term. So let's factor out that x out front, and now we have a new polynomial that's degree n minus 1. We can still factor out an x if we leave the 1 off. So let's do that. Let's factor out an x, and now we end up with an even smaller order polynomial. And we continue to do the same thing. We keep factoring out x's until we get to the very end, and we have this deeply nested polynomial that doesn't involve doing any powers. Powers actually do take more computation time than simple multiplications and additions, so that's where we're getting the benefit on this. So we'll start from the innermost part. We're going to let, again, a variable called z be a stand-in variable that we'll calculate recursively. If we start z as being n, then we're going to get a nice recursive relationship again. We'll get x times z times n minus 1, and look, there's a pattern that's developed. See if you can write down that pattern, and then you can create your code from that. Take a look at this structure and realize how it repeats, and you should be able to create your code for that. Okay? All right. And then finally, we had our extra credit problem, and we have our hints. So what we're trying to do with this extra credit is come up with a closed form solution for that sum. And then if we can get it, we'll test it using 0.5 and n equals 100 and see if we got what we did on our numeric approach. So let's see what we do with that. Well, the real hint is to look at another polynomial. We're going to factor out an x, and the reason why we're putting it in this form is that this sum has a known collapsible formula, which is 1 minus x to the n plus 1 divided by 1 minus x. And make sure you convince yourself, don't just buy into that, but demonstrate yourself that this sum actually is equal to this quotient. A way to do it would be to simply do long division of the numerator divided by the denominator, and you ought to get this series. This q now can be differentiated, and we can differentiate it in two ways. We have this sum, and I think you know how to differentiate that term, so you go ahead and do that. I think you also know how to use the product rule and the quotient rule to differentiate this form of the same function. So if we have the same function, it must have the same derivative, which means the derivatives can be set equal to each other. Try that, do some algebraic manipulation, and see if you can't get a nice clean formula for p of x.